Welcome to Lecture 8 during Week 9 on Combinational Logic Functions Minimization using Karnaugh maps. In the previous lecture, you have learned how to apply same logic circuit analysis to more complex circuits, how to synthesize logic circuits from a word description of a system, and as I've said many times in the past, any minimization was based on intuition and how much you've practiced. Now it's finally the time that you learn how to systematically approach functional minimization. The way to do that is by constructing and populating a Karnaugh map. So in this lecture, you're going to hear a series of things which are listed here. One of them is the don't care conditions, reasons with zeros in a Karnaugh map to minimize, and so forth. Before we proceed with the rest of the slides, I would like to say that if you don't understand anything from this series of slides, you're welcome to search online. Actually, this QR code will lead you to one of the, to my opinion, one of the simplest ways of explaining Karnaugh maps, which is by example. Besides this video that I recommend, others are publicly available. Feel free to search on your own. After all, it's your role as a university student to do so. So what is a Karnaugh map? You can define it by just reading these bullet points over here. What it actually is a diagram which consists of a rectangular array of squares, each of which represents a different combination of the variables that are included in a Boolean function. And the best way to explain it is by using a very simple example. So this is the truth table of an AND gate. And as you know, only min term 3 on the fourth row produces 1 as a result of the AND gate. And this is how the Karnaugh map looks like. We put y input values per row, as you see here. So the first row referred to value 0 for y, and the second row to value 1. And then we put value 0 and 1 in each of these columns for variable x. So we've split equally the variables into rows for y and columns which refer to x. As you will notice, we have marked that this particular column over here is special because for input values equal to 1, these are the results. So we just notate here this way that this is a particular row where the values of x remain the same, and not just the same, they're equal to 1. And we've done the same thing here for this row. So here we had this column, now we got this row over here, where all the values of y are not just the same, remain the same throughout the two columns, but they are also equal to 1. And obviously the contents over here are the results of the function. They represent z. You got min term 0, min term 1, min term 2, and min term 3. Now, for example, if we focus on this cell over here, min term 2, it's for input values 1, 0, 1 for x and 0 for y. So the last thing to note here is that min term 3 is what we call an implicant of z. So M3 implies Z means that if M3 is true, then Z is true. So if the min term here is true, then the function is true, which is obvious in this very simple example. Now let's do the same thing for an OR gate. This is the truth table. So the only case where you don't have 1 being produced as an output is when both inputs are 0. And this is the Karnaugh map. Now, notice one important thing here. Again, I choose to put y input values for each row and x values for each column, I could have done it the other way around. It doesn't make any difference. And here, this is how we populate it. So for inputs 0, 0, you see that the output is 0, whereas for all the other inputs, the outputs are equal to 1. For example, if we go to minterm 3, which is for input 1, 1, the output is 1. And I put it here on the Karnaugh map. Once again, any minterm that implies z, we call it an implicant. So in this example, here are all your implicants. So z, as you know, can be written in the format of a canonical sum like this, which means that the sum of products is this. It's the sum of minterm 1, 2, and 3. We know that z is the output of a two-input OR gate. You can start doing minimizations, and you will end up in this. So if you take the canonical sum here, the sum of products, and you start applying all the known theorems you know, you'll soon end up in this shrinked form of x or y. Now let's show how we use Karnaugh maps in order to avoid using intuition and minimize Boolean functions. We're going to keep the same example using the OR gate. This is the truth table and this is the Karnaugh map. What we're going to do with the Karnaugh map is that we will group together adjacent ones. Obviously, the first group is this one, and the second group is this one. If you check them out, they represent the first one, the blue one over here, represents minterms 1 and 3. And if you do a little bit of Boolean algebra math here, it ends up in y. So this one represents y. And if you do the same thing over here, this one represents x. Now, in the more general case, you try to group together the biggest number of ones that you can, as long as you can group them by powers of 2. This means groups of 2, like you have in the blue group over here or the red one, groups of 4, 8, 16, and so forth, which you will see later on with other examples, which are using bigger Karnaugh maps. By saying it's a power of 2, this means that you cannot group together 3, 5, 6, and so forth. Now take a moment and think if it is possible to group a single one. As I said, you can group 2, 4, 8, 16 together. Can you group a single one? The answer is yes, because 1 is again a power of 2. It's actually 2 in the power of 0. So bear that in mind. And the last thing to remind to everyone, as I said earlier, you don't just group adjacent ones, you group the maximum number of ones you can, of adjacent ones that you can in one group. Now, let us take again a more thorough look into our example. We've grouped together adjacent ones, and we identified 2 different groups. The blue one for y, and the the red one for x. So if we focus on the red one over here, the first one over here is this minterm. It's minterm x times y dash, obviously because the value of y here is 0, which is an implicant. And then the other implicant is this one over here, which is mapped to y times y, x times y, which is again an implicant. Now, if you do the math between the two together, and if you use the theorems that you're already aware of, Those two together give you an x, which means that x is a prime implicant. Exactly the same thing applies for the blue group. That gives you y, which is a prime implicant as well. Now again, the same Karnaugh map, only in this case, we visually represent what we said earlier. Now, you may wonder how you deal with more complicated functions, functions that have more than two input variables. Well, in this case, this is what you do. If you have three variables, one of the dimensions will refer to one of the variables. In this case, I've chosen in this example to put z for the rows, and then all the possible combinations of x, y will give you the columns. So you got 0, 0 here, 0, 1, 1, 1, and 1, 0. Now, a few things to say here. Just like I've chosen to have 2 rows and 4 columns, I could have chosen to populate a Karnaugh map that has 2 columns and 4 rows. This means that you can choose how to place the variables here, the input variables, in any possible combination that you want. The second thing is that I've marked here that these 2 columns are 2 columns where the value of x is equal to 1. Same thing for here. This is one row where z is always equal to 1, and this is a set of values where the input variable y is equal to 1. As you can see here, these 2 rows. And you'll see later on why this is important. Just a small comment here. By doing so, we have a sort of a gray code. As you can see, only 1 bit changes at a time. From here to here, only 1 bit changes. From here to here, only 1 bit changes. And from here to here, only 1 bit changes. Now let us use the same Karnaugh map, and this time we're going to go through all the steps for doing the minimization. This is the first group. As I told you earlier, yes, it can happen. You can have a single one as long as all of its neighbors are not equal to 1, so you cannot group it together with other ones. In this particular case, mean term 2 has mean term 0, 6, and 3 being its adjacent ones, but they're equal to 0. So it forms its own group. The reason why I'm using x dash here is because variable x for this particular group keeps the same value and it's always 0. So it's going to be x dash. I'm using y because y for this particular group is always equal to 1. And I'm using z obviously because for this particular group, the value of z is always equal to 0. Focusing now on this particular group, we are using x times z because x is always equal to 1. Z is always equal to 1. And we are ignoring y because its value is irrelevant because it changes from 1 to 0. The intuition behind this is that if y changes its value, it won't affect the result of the function. And this is the final group. Now, some of you might have thought that this is the last group we're looking for, but yes, now you know that this cell with this cell in particular, they are adjacent. Just like this cell over here with this one, they are adjacent. Well, not just because they are next to each other, but because this one is always with, if you wrap it up with the one on top. Okay, so using exactly the same rationale as before, we are ignoring x because x is equal to 1 here, but it's equal to 0 here, so its value is irrelevant. We're using y dash because consistently y is equal to 0 for this one and equal to 0 for this one as well. And we're using z because it's always equal to 1. So by following these very simple algorithmic steps, we managed to minimize the function. And these points over here sum up the process we followed. Some of the highlights include that cells 5 and 1 are adjacent, and that a cell containing 1 with no adjacent cell, just like the green one over here, is what we call a prime implicant. And there's a last thing here, which is also a highlight. A cell can be included in 2 different prime implicants. As I told you earlier, the way that you construct your Karnaugh map is not a standard one. Like here, I decided to use for the rows variable x, and for the columns, the combination of z and y. In this case, we end up with the minterms that you can see here. Using these minterms, this is the green group, same as it was before. This is the red group, and this is the blue group, which justifies why the adjacent cells in the previous Karnaugh map, the way we constructed it for the blue group, was by wrapping the 2 sides so that we can have minterms 1 and 5 being considered as a single group. And once again here, a little bit different. This time what changes compared to this Karnaugh map is that I'm combining y and z instead of z and y, which changes things a little bit. Again, the blue group, the red one, and the green one here. So be careful with populating the cells with ones. You always look for adjacent ones, and you try to group as many ones as possible together. One of the most difficult Boolean algebra theorems to use is the consensus theorem. And here it is. Now, if you use a Karnaugh map, you'll see that it's very easy to prove. Now, notice that these 2 groups that I've marked here, they are the essential prime implicants, which implies that there are also non-essential ones. The green group over here represents a case of a non-essential prime implicant. They are not essential because these ones are already included in 2 different separate groups. And obviously, by using the blue and the red group, here it's more clear, you end up improving the consensus theorem. Now notice that the non-essential one, the green one, is on the left side. It's not essential because although it doesn't hurt if you put it in, if you omit it, it gives you exactly the same, it gives you an equivalent result. So when you try to minimize, you consider the essential prime implicants, like on the right side of the consensus theorem. So let's see an example. Let's try to simplify this particular logic function. As you can see, the function is given to you in the form of a canonical sum. So you already know that the ones that you have to put here are for minterm 3, 4, 6, and 7. Now, check out what happens here. You can group together in the red group this cell and this cell, because as we said, they are adjacent. You can also group together these 2 ones over here, which represents the blue group. And you can also have a green group over here, but it's not an essential one. The essential ones are the blue and the red one, which is why you can always write F this way, but you can omit the green one. Again, if we write things more clearly, the essential mean terms are grouped here together and used in the minimized form of the function. What we've done is that we minimize the sum of products by inspecting the Karnaugh map and selecting only the essential prime implicants. In this example, the blue and the red. Now let's simplify this function. Actually, this function may ring a bell to you because in one of our past lectures, we've discussed a function which identifies prime numbers like 2, 3, 5, and 7. In other words, numbers that can be divided only within their own self and 1, and also identifies 1. So this is the sum of products. And by knowing the mean terms which are used here, you can populate this Karnaugh map. And now it's time to identify some groups. Obviously, that's a first group that you can identify, the red one. And one way could be by grouping together in a blue group those 4 here. So if you do these 4 ones separately, and you write things down, and then you try to minimize, you'll soon end up in this form. But you could have done things faster if you grouped all these 4 ones together. Why? Because as I said, if you try to minimize using the Karnaugh map, you always target groups that have the biggest number of ones grouped together. Now, why is this blue group giving you straight a Z here? Well, the reason is because Z has the same value, which is always equal to 1. Then you don't use Y because its value changes from 0 to 1. And for the same reason, you don't use X because its value changes from 0 to 1. In other words, Z is needed here. The other 2 variables are irrelevant. And of course, you also keep the red group. And you can also have a green one over here, which would give you an alternative. So in this case, you would use the blue group and the green one, which is also correct. But as you can notice, in this particular case, you need to do some further simplifications, which end up in a more minimized format. Again, the same as the one that you found earlier. You could have skipped those steps if you had focused on the red group instead of the green one by saying that the red group has more mean terms grouped together. Now let us try to minimize this function over here. Okay, these are the groups that we're using here. The ones over here are grouped together with the ones here because they are adjacent, as you should know by now. And we also group in the blue group those 2 ones here. And the result is this. Z dash for the red group, because Z remains consistently equal to 0 and the other 2 variables change their values, so they are relevant. And that's obviously the result for the blue group. And the take-home message is in these 2 bullet points over here. A minimum sum of products is obtained by inspecting the Karnaugh map, like we did here, and selecting all essential prime implicants, the red and the blue. Second point is that prime implicants are obtained by grouping 2 in the power of n adjacent cells containing 1s. Now let us see what happens when you're having more than 3 variables, let's say 4 variables. In this case, we group together we choose to group together Y and Z for the rows and W and X for the columns. We mark down that these are the two columns that, for instance, W remains the same and equal to 1. This is for Z. These are the two rows where Z remains equal to 1. The same for X here for these two columns and for these two last rows for Y. And this is an example of a truth table that you can have for these 4 input variables. The arrows denote where the mean terms are mapped. Now, let's not focus further on this particular example because that was just an introduction. The point here is that you see that the mean terms are not put in a sequence. So you jump from 0 to 4 to 12, and you got 8. And the final one, the 15th, is over here. So you have to be careful when you populate the Karnaugh map. Again, by using variable notation for each of the mean terms. Now, let us focus on this example with 4 input variables. This is exactly the same function that was given to you in the previous lecture, trying to identify prime numbers, including 1, from 1 to 13. This is obviously the truth table. So for each of the mean terms included here, you put 1 as the output of the function. And this is the sum of products. Now, if you try to use the sum of products so that you construct a 2-level circuit where you got your AND gates here, each for each mean term, and finally you got the OR gate here. This is how it would look for the prime numbers. So for instance, for the first mean term used, which is for number 1, this is the AND gate that is being used. And you can do the same thing for all the other mean terms here. Now let's continue a little bit more on this example and try to minimize this function. This is the Karnaugh map, which you should have ended up with after being very carefully populating it. And now what we do is that we try to identify the biggest possible groups of adjacent ones. And here it is. The first group to identify is this one. Another group is this one. Obviously, this cell over here is adjacent to this one over here. And don't get confused. This last one that remains is not a group on its own because it has an adjacent one being equal to 1. So we group these two together. And what you see here is for each group what they represent. So once you use the prime implicants, you end up with a minimized circuit that looks like this. As we've said in the previous lecture, you are never going to minimize it into less than 2 layers. However, you have managed to minimize the cost of constructing it because you're using less AND gates than what you've seen in the previous slide. Now let us try to simplify this function. We need first to construct the Karnaugh map. And after constructing it, we try to group together all the ones that we can. So the biggest group of ones that you can have here is obviously the one that contains 8 adjacent ones. The only thing that remains unchanged here is the value of y, and in this particular case, it's for y equal to 0. So we're going to use y dash for the red group. 2 other groups are the blue and the green one over here. and this is what they give us. Now the question is, are these prime implicants? Well, what about trying to group as the green group these two with these two, and these two over here, the blue ones, with these two? The difference from the previous slide is that in this case, I'm not just grouping together adjacent ones, but the biggest possible number of adjacent ones. If you compare the result with the previous slide, you see that the minimized form is actually smaller. So this is what we're looking for. The recipe for ending up in this right use of the Karnaugh map for minimizing is to identify the distinguished cells first. Then the second step is select the associated prime implicants, and then cover the remaining cells, if any. And there are no remaining ones in this particular example, by the way. Now, sometimes, besides the function being given to you, you can also be given what we call the don't care conditions. This literally means that you don't care about their value. So for min terms 0, as you can see here, 2, and 5, we can populate in the Karnaugh map a big X here. This is not variable X, please don't confuse it with it. It means that we don't care about them. Now, from the function that was given to you, you know that min term 1, 3, 7, 11, and 15, which you identify over here. The result is 1. And now you can start using the Karnaugh map the standard way, as if the don't care conditioned min terms were 1s. So that's the first biggest group. As you can see, we're using y dash and x dash for all the reasons we explained in the previous slides, because y and x, they keep the same value, which is always equal to 0. The other two variables are relevant because they change their input value. Then the second group that you can identify is the green one over here. And there is also the red group here. And this is how you minimize this function, by considering the don't care conditions. As you can see here, the red group, which doesn't contain any don't care conditions, we can keep it. And then the green and the blue ones, we can use any of them that we want because they contain don't care conditions. So you can use the red and the blue group, as we do here, or the red and the green group, as we do here. And they are equivalent. They both represent, these two sum of products, they both represent F. Now it's time to move on with simplifying the product of sums. What we've been doing so far was simplifying the sum of products. What we need to do is to find the min terms not included in F and use them to minimize F dash. So again, this is the Karnaugh map. What we try to do is to group together the biggest possible number of adjacent zeros. This one gives you Wx. And this particular group gives you YZ. As you probably noticed by now, we use Wx because both W and X here, they have a value that remains the same all the time, and it's equal to 1. And for the same reason, we use Y and Z from the red group because their value is equal to 1, whereas for the other variables, it changes. And The final group of adjacent zeros over here for the product of sums is the black one. We are keeping x because for x the value remains always equal to 1. And we're also keeping z dash because for z the value always remains equal to 0. Now if you take a look at y and w, we ignore them because they change from 1 to 0. Okay, so zeros are grouped to minimize the sum of products. And when complemented, it gives f in the form of product of sums. So what you have here from the process that we followed is a sum of products which is equal to f dash. Obviously, if you apply De Morgan, you'll end up with the product of sums just by applying De Morgan. So f is equal to this product of sums, which is very easy to apply. And this is how you do product of sums simplification.